In this problem, we're given the waveform for the current flowing through an inductor. We want to calculate and find the waveform for the inductor voltage, and then we want to calculate how much energy stored in the inductor at t equals 3 milliseconds. Here, given the current, find the voltage, we're going to use the relationship V is equal to L di dt. We need to go through and find the expression for the inductor voltage for the different intervals of time. That's going to require us to go through and calculate expressions for the current waveform over the different intervals as well. So let's start off with the first interval, 0 to 2 milliseconds. Again, we have a straight line. Again, we remember that y is equal to mx plus b. So for our slope, we're going to have minus 5 times 10 to the minus 3 over 2 times 10 to the minus 3 minus 2.5. Now it's easy to see for this interval that the y-intercept is 0. So then the expression for the current over this interval is minus 2.5 t amps. We've got the time in milliseconds, and the current's going to come out in milliamps. Now, over the interval from 2 to 4, the current's just a constant at minus 5 milliamps. So now, over the interval from 4 to 6, again, we're going to have we have a straight line. Okay, so for 4 to 6 milliseconds. Okay, if we look at our waveform, we wind up at minus 10 milliamps, and we get there from minus 5 milliamps, and we do it over 2 milliseconds. So that's minus 2.5 for the slope. Now we need to find the y-intercept, and our expression for the current so far is minus 2.5 t plus b, and we can pick a point on here. For instance, we know at t equals 4 milliseconds the current has a value of minus 5 milliamps. So we solve and get B is equal to 5 milliamps. So then the current over this interval is minus 2.5 t plus 5 times 10 to the minus 3 amps. Now if we look at our waveform, we can see over the interval from 6 to 9, we go from minus 10 all the way up to plus 5. So now let's do the calculations for that interval. So between 6 and 9 milliseconds, okay, our slope, we wind up at 5 times 10 to the minus 3. We start off at minus 10 times minus 3. And for the time, we go from 6 milliseconds to 9 milliseconds. Our slope is 5, so our waveform is 5t plus b. Now we got to find the y-intercept, and we can see at 9 milliseconds the current is 5 milliamps. And B turns out to be minus 40 times 10 to the minus 3, so our current waveform over this interval is 5t minus 40 times 10 to the minus 3 amps. We look at our waveform then from 9 to 12, we go from 5 down to 0. So from 9 to 12 milliseconds, again, we're going to have a straight line. So our slope, we wind up at 0. Our slope is minus 5/3. Again, we got to find the y-intercept. Our straight line is minus 5/3 t plus b. We can see at 12 that we have a value of 0. So that gives us b is 20 times 10 to the minus 3. So then we have minus 5/3 t plus 20 times 10 to the minus 3. And then from the graph, obviously we can see that for t greater than 12 milliseconds, that I of t is 0. So now, we've calculated all the descriptions. Let's kind of go in and summarize them. Okay, we have minus 2.5 t and then the current is a constant. And then for the next interval, and then it's 0 for t greater than 12 milliseconds. Okay, so there's a summary of our current waveform. So now we're ready with v is equal to L di dt. Okay, so for the first interval, we have 2 times the derivative of minus 2.5 t. So that's going to give us minus 5 volts. Then for the next interval, we see we have 2 times the derivative of minus 5 times 10 to the minus 3. So that's 0. The next interval, we have this expression, so we get 2 times the derivative of minus 2.5 t plus 5 times 10 to the minus 3. So here we get 2 times minus 2.5, or minus 5. So that gets us through 3 of our 6 intervals. So then for the next interval, we have 2 times the derivative of 5t minus 40 times 10 to the minus 3. So here we have 2 times 5, 10. So that's what it is between 6 and 9 milliseconds. Now we have minus 5/3 t plus 20 times 10 to the minus 3, and we're going to take the derivative of that. So now we have 2 times minus 5/3, which is minus 3.33 volts. And then v of t is 0 for t greater than 12 milliseconds. So now we could take and sketch that. So we got it over our different intervals. So let's sketch the inductor voltage. 10 minus 5, and let's see, we have 2, 4, 6, 9, and then 12. So we start off at minus 5 for 0 to 2 milliseconds. Then it's 0, okay, from 2 to 4. Then we're back to minus 5 from 4 to 6. Then we're going to jump up to 10. We're going to be 10 from 6 to 9. Then we're going to jump down to minus 3.33, and then we wind up at 0. So this is minus 3.33. Now we've got one last calculation to make, and that's the energy stored in the inductor at t equal 3 milliseconds. And if we look at our waveform and look at where 3 milliseconds is and read down, that tells us that the current is the current is minus 5 milliamps. So the energy stored in an inductor is 1/2 Li squared. So we have 1/2 times 2 times minus 5 times 10 to the minus 3 squared. And that tells us that the energy is 25 microjoules.